Our universe is a vast and mysterious place. It's filled with billions of galaxies, each containing billions of stars. But here's the thing. The matter we can see, the stars and galaxies, only makes up a small fraction of the total mass of the universe. The rest is something else, something we can't see. We call it dark matter. Dark matter doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes. So how do we know it's there? We know because of its gravity. Dark matter's gravity affects the way galaxies rotate and the way light bends around massive objects. Imagine a spinning top. If you only see the top part, you might think it should fly apart. But it doesn't because of the hidden weight and force holding it together. Dark matter is like that hidden force in the universe. Dark matter is a puzzle. We know it's out there, but we don't know what it is. Understanding dark matter is one of the biggest challenges in astrophysics today. The first clues about dark matter came from studying the rotation of galaxies. Astronomers expected stars farther from the center of a galaxy to move slower, just like planets farther from the sun move slower. But that's not what they observed. Instead, they found that stars on the outskirts of galaxies were moving much faster than expected. This unexpected speed suggests that there must be some invisible matter providing extra gravity to hold these stars in their orbits. Another piece of evidence comes from galaxy clusters. These are huge collections of galaxies bound together by gravity. By studying the motions of galaxies within these clusters, astronomers can estimate the total mass of the cluster. These estimates show that the mass of a galaxy cluster is far greater than the mass of its visible stars and gas. This discrepancy provides further evidence for the existence of dark matter. Finally, the phenomenon of gravitational lensing also supports the existence of dark matter. Einstein's theory of general relativity predicts that massive objects can bend the path of light passing by them. Astronomers have observed light from distant galaxies being bent around massive galaxy clusters, creating distorted and magnified images. The amount of bending observed is greater than can be explained by the visible matter in the clusters, indicating the presence of dark matter. So, if we can't see dark matter, how can we figure out what it's made of? Scientists have proposed several candidates for dark matter particles. One of the leading candidates is called a WIMP, which stands for Weakly Interacting Massive Particle. WIMPs are hypothetical particles that interact with normal matter through the weak force, which is responsible for radioactive decay. This weak interaction is why WIMPs would be difficult to detect directly. They would pass through ordinary matter, including our detectors, without leaving much of a trace. Another candidate is the axion, a hypothetical particle that was originally proposed to solve a problem in particle physics. Axions are thought to be much lighter than WIMPs and would interact with matter even more weakly. Scientists are actively searching for both WIMPs and axions using a variety of experiments. Some experiments are looking for the faint signals that these particles might produce when they collide with ordinary matter. Others are trying to create dark matter particles in the laboratory. Despite decades of searching, we still haven't found any definitive evidence for WIMPs or axions. This lack of detection has led some scientists to consider alternative theories for dark matter. Some scientists believe that dark matter might not be made of particles at all. Instead, they propose that our understanding of gravity might be incomplete. These theories, known as modified Newtonian dynamics, MOND, or modified gravity, suggest that gravity behaves differently at very large distances or in regions of low acceleration. While MOND theories can explain some observations, they struggle to explain others, such as the bullet cluster observations. Furthermore, modifying gravity is a complex undertaking, and any successful theory must be consistent with all other known laws of physics. The search for dark matter continues. New telescopes and experiments are being developed with increased sensitivity and precision, pushing the boundaries of our understanding. For example, the James Webb Space Telescope, launched in 2021, is expected to provide valuable insights into the early universe and the distribution of dark matter. Ultimately, unraveling the mystery of dark matter is crucial for understanding the origin, evolution, and ultimate fate of our universe. It's a challenge that continues to captivate astronomers and physicists alike, driving us to explore the deepest realms of space and the fundamental nature of matter itself.